Okay, welcome back everyone. So in this video we'll cover the second of the three methods for solving simultaneous linear equations with matrices. This one is Cramer's rule. Let's see. So I'll do a quick derivation and state Cramer's rule formally, and then we'll use it to solve an example. So firstly, the derivation. So for the 3 by 3 case, it's going to look as follows, but it generalizes up no problem. So we consider both the set of simultaneous equations and the determinant for the matrix A. Now, if we take the set of simultaneous equations and divide through by the first unknown, so x1. Now, if we do that, we'll end up with these expressions here. On the other side, to the determinant, now one thing to recall is that we can take any amount of one row and add it on to another row, and that leaves the whole determinant unchanged. That was just one of the properties of determinants we covered last week. And so to the first row, I'm going to add x2 over x1, which is just a number, lots of the second row, and x3 over x1, lots of the third row. Now, if I do that, then the first row looks a little bit complicated. It looks like this. The second two rows, the second row and the third row, are unchanged. Now, why have I done that? The reason I've done that is because this row here is exactly the same as the left-hand side of these equations. And so I can replace the left-hand side with the right-hand side inside the matrix. So each one of these complicated-looking expressions gets replaced with x prime 1 over 1, x prime 2 over x1, and x prime 3 over x1. At that point, another property of matrices is that we can take any common factor out of a column, and that will just multiply the whole matrix by that common factor. So each of these elements in the first column has a factor of 1 over x1. So we can take that out and just multiply that on the front. So we have an expression now with x1 in it, and x1 is one of the solutions. So that's one of the unknowns that we're trying to solve for. And so we have the determinant of the matrix is the determinant of this matrix divided by that x1. And so we can just rearrange that to solve for x1. Now, these delta 1s are called the Cramer discriminants. And the 1 just refers to the fact that the first row has been replaced with the x prime vector. And you'll get a delta 2 and a delta 3 as well. The other two of the Cramer discriminants here. So we can solve for x1, x2, and x3 using these formulae, which are really just the ratio of two determinants. Okay, so let's just state that result formally. So this is Cramer's rule. It says that a set of simultaneous equations represented by matrix equation ax equals x prime is solved by these, where the delta 1, delta 2, and delta 3 are the Cramer discriminants given by the determinant of the matrix A with the ith column replaced with the vector x prime. Okay, so that's the formal statement. That's Cramer's rule. Let's use it for an example. It's actually the same example as we used with the direct inversion, so we'll be able to check we have the same answer. And so it looks like in order to solve for x1, x2, and x3, we are going to need the determinants of A and also the Cramer discriminants. So let's calculate those one by one. So firstly, the first one equals the determinant of this. So the determinant of A with the first column replaced with this vector. So like that. The second one is the determinant again of A, except this time with the second column replaced with the 1, 2, 0 x prime vector. And then finally, discriminant number 3 is the determinant of the matrix, but with the third column replaced with that vector. So 1, 2, and 0 in the third column. Okay, so we need to calculate each of these determinants. Now, it's going to speed us up that both the elements in this row are, two of the elements in this row are 0. And so we can, I guess, count along the bottom row, in which case we'll get 0, 0, and the only one that matters is the minus 1 multiplied by 1, 2, 2, 3. And do we need a negative for that? Well, this is we'll get minus 1 to the power of 3 plus 3. So this is the third row, third column. And so minus 1 to the power of 6 is 1. So we wouldn't need a minus sign there. Now that will end up as minus 1 times 3. So 3 subtract 2 times 2 is 4, giving us minus 1 times minus 1, which is 1. Okay, now for the second, there's no rows or columns here with multiple zeros in, so let's just work across the top row like we would usually do. So that'll be 1 times determinant 2, 1, 0, minus 1, subtract 1 of minus 1, 1, 2, minus 1. So that is negative 2 subtract 0, subtract 1 subtract 2 equals, so minus 2 subtract minus 1, so add 1 equals minus 1. Okay, and the third one is, again, there's 2 zeros in the bottom row here, so it's kind of along the bottom row, and the only one that'll matter is this, so we'll get 2 lots of the minor 2, 1, 3, 2. Do we need a minus sign for that? Well, it's going to be minus 1 to the power of 1 plus 3. Well, really, it's 3 plus 1. And again, that's just minus 1 to the power of an even number, so the minus disappears. So here we'll get 2 times 2 is 4. Subtract 3 times 1, so subtract 3 equals 2 times 1 is 2. Okay, and we also need the determinant of A. So let's calculate that too. Copy, paste. And so det A equals det of this thing, this matrix. Okay, let's just work along the top row for that one. So we'll get 1 times 3, 1, 0, minus 1, subtract 2 of minus 1, 1, 2, minus 1, equals 1 times minus 3, subtract 0, minus 2 times 1, subtract 2, equals, let's see, so that's minus 3, and then we're subtracting minus 1, so adding 2 equals minus 1. Okay, so we are just going to use these expressions. And we're only counting up to 3 here. It's a 3 by 3 matrix. Okay, so the 3 parts of the solution are firstly discriminant number 1 over det A. So that's 1 over minus 1. So 1 divided by minus 1 equals minus 1. And the second one was minus 1. So we'll have minus 1 divided by minus 1 equals plus 1. And then finally, the third discriminant is 2. And so we'll get 2 divided by minus 1 equals minus 2. And we should be able to verify that's x1 is minus 1, x2 is plus 1, x3 is minus 2, and that should be the same solution as we found above when we were solving by direct inversion, and it is. So minus 1, 1, and minus 2. Minus 1, 1, and minus 2. Okay, so we've done it right. In the next video, we'll solve exactly the same problem by the third method, and the third method is called Gaussian elimination. So I'll see you then.